The aircraft, automotive, and civil industries all aim to have lightweight yet strong structures while reducing production cost but without compromising the reliability or increasing the environmental cost of their products. In order to achieve this goal, these industries are taking an in-depth interest in the materials of their structures.
The structures are the basis of aerospace, civil, automotive, and many other important industries. To build these structures, conventional materials such as steel and aluminum to the advanced ones like composite materials are used. Nowadays, composite structures are used in many aspects of industrial structures due to significant advantages over isotropic materials such as greater strength, stiffness, directional properties, and lightweight. But due to their anisotropic behavior, the failure modes of these materials are more complicated than those of isotropic ones. In fact, composite structures may suffer a variety of damages that are not common in metal structures. So, despite the many benefits of composite structures, such as high particular stiffness and strength, it's likely that composites suffered from various defects such as cracks, delamination, disbond, inclusion, and so on and so forth.
With multi-advanced materials, new manufacturing and joint techniques were developed. Moreover, we still have to go further some challenges related to their application, such as the uncertainty in the prediction of their remaining useful life, since these materials present complex damage modes like delamination, matrix crack, fiber breaking, crack propagation, debonding, and others. In addition, it's still challenging to determine their quality control since mainly composites and polymeric materials present significant effects in their mechanical properties due to several environmental actions. In order to ensure the use of these new materials and joining techniques in primary structures, different approaches can be implemented to monitor their structural state. Getting inspired by the human body and or nervous system, sensors have been implemented in components to get real-time or on-demand information about the structural health state. Then, the acquired information can be saved and analyzed by the brain, that is the acquisition system, and then related processing software. Applying structural health monitoring methods, it's possible to increase safety, reliability of the monitored components. In addition, it aids in saving life cycle costs by avoiding redundant stopping for periodic inspection and increases their efficiency.
Is there any way to discover and monitor these damages without an interruption in daily operation of the system? The answer is yes. Structural health monitoring is to acquire and analyze data which brings ability to observe and characterize the health state of the structure. As an example, let's consider the life cycle of an aircraft from the health stage to an end of life. Aeronautic composite parts are required to be life cycle managed under damage tolerance principle and the safe life, while airworthiness is maintained through the process of scheduled inspection and, if needed, repair or replacement. However, structural health monitoring systems can provide information about the health state of the structure from onboard sensors in the sense of diagnostic, in terms of detection, localization, and severity. Prognosis, which addresses to prediction remaining useful life in terms of remaining life cycles until a threshold event. Rule can be the input for condition-based maintenance strategies and also for decision-making processes. In conclusion, we can put in words that human interaction, time consumption, and overall cost can be reduced within the framework of structural health monitoring and condition-based maintenance.
When data are acquired from sensing technology, they usually come with a lot of noise. Noise can be added also by external factors, such as the environmental conditions that the structure is working with. This means that running the same experiment many times will give us different measurements. Therefore, we can say that we have an uncertainty in our data. The uncertainty that makes each run of the experiment slightly different from the others is called aleatoric uncertainty and cannot be neglected. There is also the epistemic uncertainty, which is related to inaccurate sensor measurements or to the model's imperfections. This kind of uncertainty could be reduced by acquiring more data or by creating better models. So, how to deal with the total uncertainty? Should we reduce it, or should we consider it with our outputs as a measure of randomness? Uncertainty is one of the reasons that there is still a huge gap between theory and practice. Models without considering the uncertainty usually are very optimistic about their outputs and often fail in real case scenarios, especially in problems that prioritize human safety, such as in the aircraft industries.
Hi, I'm Thanos Kontogiannis, PhD researcher at the Faculty of Aerospace Engineering of TU Delft. I work with the Pythia team at the Center of Excellence in AI for Structures. My research, which is also part of the DepMat project, focuses on the next step after data acquisition and processing, which is the diagnosis of the state of the system, utilizing indirect measurements such as SHM data, and also its integration to a closed-loop framework towards creating self-aware, intelligent systems that can monitor their state and make decisions on either altering their operational conditions without compromising their mission, and eventually even plan their maintenance schedule.
I'm Mortaza Moradi, PhD researcher at TU Delft, Faculty of Aerospace Engineering. I'm working in structural integrity and composites, and also Center of Excellence in Artificial Intelligence for Structures, Prognostic, and Health Management. The subject that I'm working on is intelligent feature extraction and fusion for designing prognostic parameter utilizing structural host monitoring data. My subject is a part of bigger project, ENHANCE, European Trained Network Intelligent Prognostics and Health Management in Composite Structures. ENHANCE is a Marie Curie innovative training network for early stage researchers funded by the European Commission. I'm interested in topics such as structural host monitoring and non-destructive testing, especially acoustic emission, land wave, and thermography, with focus on composite structures, and of course, by using artificial intelligence, information fusion, signal, and image processing.
Hi everyone, my name is Rosemary Lima, and I'm a PhD candidate in mechanical engineer from Politecnico di Milano. And my research topic is about advanced methods for monitoring adhesively bonded joints. I mainly work with optical fibers back strain monitoring and acoustic emission in double cantilever beam joints under quasi-statically and fatigue mode 1 loading.
Hey to everyone, I'm Panos, and I'm also a member of the Structural Integrity and Composites group in the Faculty of Aerospace Engineering. My contribution derives from my PhD, which is focused on post-prognosis decision-making utilizing machine learning techniques. Generally, my research belongs to the last part of our entire mission as a team, right after the prognosis phase, and is highly related to practical data-driven methods for decision-making under the concept of the Fourth Industrial Revolution. This work is also a part of the Morpho European project.
Hello, my name is George Galanopoulos, and I am a postdoctoral researcher at the Aerospace and Structural Materials Group at the Faculty of Aerospace Engineering at TU Delft. The field of my research is structural health monitoring, starting from the experimental part all the way to the remaining useful life prognosis part. The core of my work focuses on the feature extraction, where suitable features are discovered from the raw data to increase the accuracy of the diagnostic and prognostic algorithms. Currently, I am working on aerospace turbine blades as part of the European-funded project Morpho.
Hello everyone, I am Ferda Cansugül. I am PhD candidate in Structural Integrity and Composites group at Aerospace Faculty in TU Delft and working as doctoral researcher at Safran. In my research subject, I mainly concentrate on Galloway-based structural health monitoring techniques to monitor aerospace structures during their life cycle and predict their remaining useful life by using structural health monitoring data. It's very exciting to explore my topic deeply with the expertise of TU Delft and Safran under the project of Marie Curie guided waves for SHM.
I'm Mariana Salinas Camus, PhD researcher at TU Delft in the Faculty of Aerospace Engineering in the Department of Structures and Materials, and I'm also affiliated to the Center of Excellence in Artificial Intelligence for Structures. My topic of research is adaptive prognostics for remaining useful life of engineering systems.
Hello, my name is Stratos Koufis, and I'm a PhD candidate in the Aerospace Structures and Materials Department at Delft University of Technology. Together, we will see how we can expand the use of structural health monitoring techniques into the repair processes. My research focuses on the process monitoring of the cold spray process, a solid-state deposition technique for repair applications in the aviation industry. The monitoring is done using the airborne acoustic emission of the process. The project is under the Bright Sky Fund and the first work package that is about maintenance, repair, and overhaul of aircrafts.
Among SHM techniques, acoustic emission is extensively used due to its advantages for in situ damage monitoring with high sensitivity and its capability to continuously inspect a relatively large area. This technique is defined as a transmission of an elastic stress wave through the material, which is usually originated from an internal source such as crack initiation and growth. So in acoustic emission, which is a passive SHM technique, there is no external sources to excite the material, but the sources are inside the material. These sources may be damage initiation and propagation, plastic deformation, internal friction, and so on and so forth. The superiority of the passive techniques over the active ones, which need an external excitation source, is their capability for structural health monitoring while the structure is in operation. As you can see in this figure, the necessary devices to perform this monitoring technique consists of a network of acoustic emission sensors, of course, to capture the microscopic surface vibrations of the structure and convert them to analog signals. Then preamplifiers, which magnify the intensity of the analog signals. And then acquisition section, where the amplified signals are recorded and converted from the analog to digital signals. And finally, data processing section, where the recorded digital acoustic emission waveforms are analyzed. Acoustic emission analysis are usually performed using its waveforms or the features extracted from these waveforms. Figure 2 shows a typical acoustic emission waveform and its features. As you can see in figure 3, since the 1970s, there is an increasing trend to use acoustic emission for damage assessment of composite structures, especially during the last decade. During these 5 decades, around 1,000 papers have been published on this topic.
Ultrasonic guided waves. In order to achieve a reliable and sensitive structural health monitoring analysis, recorded past data of the structure is crucial. For composite materials, the past data can be recorded by SHM, and guided waves are one of the active monitoring techniques that allow to conduct inspections in chosen intervals. They consisted of longitudinal and transfer waveforms, and structure can be examined using ultrasonic guided waves owing to their characteristic scattering and mode conversion originated as structural discontinuity produced by the damage. The whole area of the structure can be analyzed by using specially arranged sensors to excite and receive guided waves. Guided waves do not only carry the information related to damage but also contain signals that interfere because of the reflection and scattering phenomena due to structural boundaries. As a result, finding the damage-related signals is a challenging process, and therefore a data processing step is essential to achieve that information.
How about optical fibers? Among the different types of sensors available for implementation in the structural health monitoring systems, fiber optics are commonly used. The main advantages of them are their low evasiveness, weight, and energy required for operation when compared to strain gates or piezoelectric transducers. In addition, they present greater accuracy and long-term stability. Optical fibers are filaments made by dielectric materials that conduct high-frequency electromagnetic radiation, it means light, with the lowest losses. The light has a guided propagation inside the optical fiber's core, obtaining a total inner reflection between core and cladding. So, When the optical fibers are applied as sensors, they produce modulated optical signals that can give relevant information about the health state of the structure by variations in the signal response. There are two main types of monitoring using optical fibers: by local or distributed sensing mechanisms. For example, if we have a crack propagation inside the structure, the main response of the optical fiber signals will change the intensity and position, giving us relevant information about the damage propagation.
The idea of data-driven arose from the broader topic of data analytics, particularly in the business world. Nowadays, AI is applied in every application. AI succeeds when the training sets lack enough physics and rely on the historical and present data to create a model to predict results, such as driverless automobiles, autopilot flights, and structural health monitoring, etc. It contains offline learning and testing of models, as well as online real-time operation of those models, and in some situations, real-time updates of models based on new data observed in the field. AI algorithms can be either deterministic or non-deterministic. Machine learning, evolutionary computation approaches, and probabilistic methods are examples of common AI tools. Machine learning algorithms that are commonly used are supervised, unsupervised, and reinforcement learning. In the era of the fourth industrial revolution of big data, AI is widely used in every field of composite structures, including design analysis, manufacturing, non-destructive testing, structural health monitoring, and of course, prognostics of its remaining useful life, material state, and damage modes. Here you can see a pie chart on SHM and NDT sensor systems used along with AI in composites.
In complex structures, such as the aerospace structures, where accurately modeling the degradation through physical models is difficult, data-driven methodologies are usually preferred for the prognostic tasks. These methodologies rely on the existence of damage-sensitive features known as health indicators. The quality of these health indicators greatly affects the prognostic models. Briefly, health indicators are features capable of capturing the degradation of the structure. They can either be directly derived from physical properties like strain or temperature, or constructed using advanced processing methodologies like artificial intelligence or genetic programming. Their suitability is measured using three attributes: monotonicity, prognosability, and trendability, each one commenting on a different property of the health indicators. High scores on all these attributes increase the prognostic potential of health indicators for accurate prognostics.
In structural health monitoring, we have the diagnostic and prognostic phase. So let's talk about the diagnostic phase. The main advantage of structural health monitoring methods compared to non-destructive techniques is the possibility of real-time or on-demand monitoring of in-service structures, followed by feature extraction and data analysis phase, where damage zones in large assembly structures can be identified, located, and sometimes also quantified. Furthermore, an operational history of the monitored systems is created, allowing a maintenance plan based on the structure's actual state instead of predefined service interruptions, and consequently, a reduction of their maintenance costs can be observed.
During data acquisition, generally two types of data are generated: labeled and unlabeled, depending on whether information about the actual state of the system is captured and paired with the SHM data or not. Unlabeled data are usually abundant, easy to acquire, and don't require expert knowledge, whereas labeled data are usually acquired through costly and time-consuming experiments, also conducted by experts. This is the main reason that labeled data, especially for aerospace applications, are very limited, while an abundance of unlabeled data can be captured during the operation of the system. The gold standard, mainly due to their high achievable accuracy when it comes to data-driven diagnostics models, are the supervised machine learning-based ones, which are trained only with labeled data. Unlabeled data by definition cannot be used with supervised learning algorithms, and thus the information that is contained in them is not utilized, leaving researchers with no other choice rather than trying to gather even more labeled data. This is where my research falls in, with the goal to explore and utilize the overlooked information contained in the unlabeled data in order to improve the diagnostics model's performance. To achieve this, semi-supervised learning algorithms are being explored.
According to International Organization for Standardization, prognostic is defined as the estimation of time to failure and risk for one or more existing and future failure modes. This task is composed of two steps. The first step is to identify the current level of health, which can be considered as detection and diagnosis. The second step is to predict health indicators in order to calculate and estimate remaining useful life. Basically, due to intrinsic uncertainties in degradation process, measurements, operating environments, and modeling errors, multiple sources of uncertainty should be quantified in order to provide reliability in predictions and remaining useful life calculation. Instead of a single number, the decisions are dependent on the range of remaining useful life confidence. Narrow confidence represents greater precision performance than broader confidence, which reflects high uncertainty, so unsafe decisions should be avoided.
Now we have the data which is obtained through all the different SHM techniques that we mentioned so far. And our purpose is to work through feature extraction and fusion, rule regression, and damage classification. But how? Well, artificial intelligence techniques show strong potential by their modeling capabilities of nonlinear data, so that by using methodologies of artificial intelligence, autonomous models and predictions can be achieved. When it comes to the prognostic of remaining useful life, this can be considered as a regression task. During the lifetime, the structure will face degradation of its properties, and remaining useful life can be predicted until a critical level before the final failure. If we would calculate the remaining useful life for the time that is acquired at the beginning of the lifetime, it is possible to have limited number of data and make a prediction for remaining useful life later than actual rule time. However, within the time, as much as we continue to obtain more data, our model can take us to a more precise prediction, which can predict critical level of degradation before final failure occurs.
Engineering systems degrade over time, and the process of degradation changes depending on which system or material we are studying, and also due to the environmental conditions. For example, if we have a turbofan, we can use the data coming from the sensors to make a health assessment of the component, and we can also do a prediction of how many hours or days the turbofan can stay in service. This information is crucial to make decisions about the system and to perform predictive maintenance. Currently, there are different approaches to perform prognostics of engineering systems. However, what will happen if an aircraft faces unexpected phenomena such as a bird strike? Will these prognostics models be able to make a reliable prediction of the health of the system? And that's why we need models that can adapt to unexpected phenomena, or in other words, to new data that the model was not trained with. Therefore, my research is focused on developing an adaptive model by using artificial intelligence.
Decision-making is a very interesting and active research field, and despite its long history, its application to engineering systems is still a challenge. The integration of AI and machine learning into the decision theory creates new decision strategies that better face real-world problems. So, how is the decision-making related to the PHM? If one goes back to the prognosis phase, he will have a measure of the structure's current and future condition, usually in terms of remaining useful life. Then, what should we do with this information? There is a reason of reading the prognostics information, and that is because engineers have to make a decision related to when and how should they maintain the structure. This kind of decision-making that uses the prognostics information is called post-prognosis decision-making, and it's still at its infancy. A huge challenge of this field is how to make a decision-making system capable of looking as far as possible into the future. Things become even worse in real-world problems where the maintenance process, such as repairing a component, is not always ideal and unexpected problems may occur during the maintenance. If the uncertainty from the remaining useful life predictions is added to the above difficulties, then creating an efficient decision-making system becomes a real challenge. Fortunately, by managing the induced uncertainty and by applying machine learning methods, one could create powerful post-prognosis decision-making systems which could assist human experts in choosing optimal decisions in the means of a human-machine interface.
When the decision to repair a component has been made, we need to ensure that the repair process that we use operates with high consistency and that the final product meets all the quality requirements. But first, let's see what type of repairs we can perform with cold spray. Let's assume that we have this fastener hole with visible damage on the surface. First, we need to blend the damage, then we fill in the gap that we have created with cold spray, and finally, machining is done to meet the dimensional and surface requirements. To perform cold spray, we need a nozzle that accelerates a gas to supersonic velocity and a powder feeder that fits the powder in the nozzle. Motivated by the fact that experienced users of the equipment could identify process-related problems from the sound of the process, a microphone is used to capture the airborne acoustic emission. The aim is to perform a diagnosis of the process conditions and the health condition of the nozzle that tends to wear down with use. This data is used to diagnose material properties of the deposition, such as porosity and hardness, that are crucial for the quality of the repair and consequently the acceptance or rejection of the repaired part.